one of the key topics in physics. Everything in the universe moves.
How?
It might only be a small amount of movement and very, very slow, but movement does happen.
But I am not in motion.
Even if you appear to be standing still, the earth is moving around the sun and the sun is moving around our galaxy.
Mom, I want to know more about motion. Please tell me.
Okay, let's go home. I will teach you about motion.
Objectives. At the end of this lesson, you'll be able to define motion, describe motion along a straight line, understand uniform and non-uniform motion, calculate speed, define and calculate velocity, define acceleration, understand the graphical representation of motion, explain uniform circular motion. Understanding motion. Motion is relative to the position of the observer. For example, you can see that an automobile is moving with respect to the ground. Different observers may perceive the motion of an object in an entirely different way. Or we can say that an object is in motion if its position changes with respect to an observer. A rocking chair, a swing, a bouncing ball are the examples of things that assist motion. The Earth in its orbit around the Sun is also said to be in motion. Motion along a straight line. Everything in our world moves. Even stationary things such as your house move in relation to the sun or to the other stars. The motion may be purely vertical, that of a falling stone, purely horizontal, that of a car on a level highway, or slanted, that of an airplane rising at an angle from a runway, but it must be a straight line. When we try to locate an object in physics, we will usually relate it to some sort of reference point. This point is usually the origin, the 0 point of an axis, x, y, or z. Furthermore, we provide a numeric representation for an object's location by placing it either in the positive direction or negative direction in relation to that reference point. For example, let's put a particle at x is equal to 10 meters. The particle would then be located at 10 meters from the origin on the x-axis. As you may have noticed, position is marked by some unit of length. The typical unit we will use is meters. Here the distance covered by the object is 10 meters. To describe distance, we need to specify only the numerical value and not the direction of motion. The numerical value of a physical quantity is its magnitude. The difference between an object's starting position and final position after it moves is known as displacement. Uniform motion and non-uniform motion. To understand uniform and non-uniform motion, let's take one example. Look at this table. This is the distance covered by a car A. We can see that in 0 seconds it covers 0 meters. In 5 seconds it covers 10 meters. In 10 seconds it covers 20 meters and so on. Or we can say that in every 5 seconds, it covers 10 meters. It travels equal distances in equal intervals of time. Hence, it is in uniform motion. Look at car B now. Car B covers 5 meters in 5 seconds, 15 meters in 10 seconds, 20 meters in 15 seconds. We have seen that the car B does not cover equal distances in equal intervals of time. Therefore, it is in non-uniform motion. Speed. Now, can you tell the difference between two identical objects traveling at different speeds? Nearly everyone knows that the one moving faster or the one with a greater speed will go farther than the one moving slower in the same amount of time. Whatever speed is, it involves both distance and time. Faster means either farther, great distance, or sooner, less time. Doubling one's speed would mean doubling one's distance traveled in a given amount of time. Doubling one's speed would also mean halving the time required to travel a given distance. The rate of motion of an object can be measured by finding out the distance traveled by the object in unit time. The SI unit of speed is meter per second. This is represented by this symbol. In most cases, objects will be in non-uniform motion. Therefore, we describe the rate of motion of such objects in terms of their average speed. The average speed of an object is obtained by dividing the total distance traveled by the total time taken. If an object travels a distance s in time t, then its speed v is equal to s upon t. Speed with direction. Velocity is speed in a given direction. Speed describes only how fast an object is moving, whereas velocity gives both the speed and direction of the object's motion. To have a constant velocity, an object must have a constant speed and motion in a constant direction. It is calculated in the same way as we calculate average speed. It is given by the arithmetic mean of initial velocity and final velocity for a given period of time. That is, average velocity is equal to initial velocity plus final velocity by 2. Where VAV is the average velocity, U is the initial velocity, and V is the final velocity of the object. Speed and velocity have the same units, that is, meter per second. Rate of change of velocity. Acceleration is the rate of change of velocity with time. In one dimension, acceleration is the rate at which something speeds up or slows down. Acceleration describes the rate of change of both the magnitude and the direction of velocity. In SI units, acceleration is measured in meters per second square. It is a measure of the change in the velocity of an object per unit time. That is, acceleration is equal to change in velocity by time taken. If the velocity of an object changes from an initial value u to the final value v in time t, the acceleration a is v minus u upon t. Uniform or constant acceleration is a type of motion in which the velocity of an object changes by an equal amount in every equal time period. On the other hand, an object can travel with non-uniform acceleration if its velocity changes at a non-uniform rate. Example. Let us take the example of a racing car. It takes 10 minutes or 0.17 hours to travel 23 kilometers from start to finish. We have to find the average speed and average velocity. We know that average speed is distance traveled by time taken. Therefore, average speed is equal to 23 kilometers by 0.17 hours, which is equal to 135.29 kilometers per hour. Similarly, average velocity is displacement by time taken. We can see in the picture that displacement is 4 kilometers. Therefore, average velocity is equal to 4 kilometers by 0.17 hours, which is equal to 23.53 kilometers per hour. Graphical representation of motion. A graph is a pictorial representation of the relation between two sets of data, of which one set is of dependent variables and the other set is of independent variables. In a displacement time graph, displacement is a dependent quantity taken on the y-axis and time is taken on the x-axis as it is independent. If the position of an object changes with time, it is said to be in motion. If an object has equal displacements in equal intervals of time, then the graph is a straight line inclined with the x-axis, which represents uniform motion of the object. If the graph is a curve, it represents non-uniform motion. The slope of displacement time graph gives velocity of the object. We will go through this in detail after a short interactivity. Distance time graphs. Plotting distance against time can tell you a lot about motion. Let's look at the axes. Time is always plotted on the x-axis, bottom of the graph. The further to the right on the axis, the longer the time from the start. Distance is plotted on the y-axis, side of the graph. The higher the graph, the further from the start. If an object is not moving, a horizontal line is shown on a distance time graph. We can see that the time is increasing to the right, but its distance does not change. It is not moving. We say it is at rest. If an object is moving at a constant speed, it means it has the same increase in distance in a given time. In the graph we can see that time is increasing to the right and distance is increasing constantly with time. This means the object moves to a constant speed. Constant speed is shown by straight lines on a graph. Velocity time graphs. Velocity time graphs are also called speed time graphs. Speed time graphs look much like distance time graphs. Time is plotted on the x-axis. Speed or velocity is plotted on the y-axis. A straight horizontal line on a speed time graph means that speed is constant. It is not changing over time. This graph shows increasing speed. The moving object is accelerating. This graph shows decreasing speed. The moving object is decelerating. This is a velocity time graphs of an object in non-uniformly accelerated motion. Equations of motion by graphical method. The three equations of motion are: v is equal to u plus at, s is equal to ut plus 1 upon 2at square, 2as is equal to v square minus u square, where u is the initial velocity of the object, which moves with uniform acceleration a for time t. V is the final velocity, and s is the distance traveled by the object in time t. This equation describes the velocity-time relation. This equation represents the position-time relation. This represents the relation between the position and the velocity and can be obtained from these two equations. Let us go through them one by one. Equation for velocity-time relation. Consider an object moving with a uniform velocity u in a straight line. Let it be given a uniform acceleration a at time t is equal to 0 when its initial velocity is u. As a result of the acceleration, its velocity increases to v, final velocity in time t, and s is the distance covered by the object in time t. The figure shows the velocity-time graph of the motion of the object. Slope of the vt graph gives the acceleration of the moving object. Thus, acceleration is equal to slope, which equals ab, which equals bc upon ac, which is equal to v minus u whole upon t minus o, where a is equal to v minus u whole upon t. This equals v minus u equal to at. V equals u plus at, which is the first equation of motion. Equation for position-time relation. Let the distance traveled by an object is s in time t and acceleration a. we can see that the distance traveled by the object is obtained by the area enclosed within. Therefore, distance traveled, S, is equal to area of the trapezium ABDO, which equals area of rectangle ACDO, plus area of triangle ABC, which is equal to OD into OA plus 1 upon 2BC into AC. Now putting the values, we get T into U plus 1 upon 2 into V minus U into T. On solving further, we get UT plus 1 upon 2 into V minus U into T. Now from the first equation we know that V minus U is equal to AT, or we can write V is equal to U plus AT. Therefore, S is equal to UT plus 1 upon 2 AT square. This is the second equation of motion. Equation for position-velocity relation. The third equation will be obtained from these two equations. From the velocity time graph, distance traveled S is equal to area of the trapezium OABD. This is 1 upon 2 into B1 plus B2 whole into H, which is equal to 1 upon 2 into OA plus BD whole into AC. Substituting OA by U, BD by V, and AC by T, we get S is equal to 1 upon 2 into U plus V whole into T, equation 1. But we know that A is equal to V minus U whole upon T, or T is equal to V minus U whole upon A. Substituting the value of T in equation 1, we get V square minus U square is equal to 2AS. 2AS is equal to V plus U into V minus U. V plus U into V minus U is equal to 2AS. By using the identity A square minus B square is equal to A plus B into A minus B, we get V square minus U square is equal to 2AS. This is the third equation of motion. Uniform circular motion. Uniform circular motion describes the motion of a body traversing a circular path at a constant speed. The distance of the body from the axis of rotation remains constant at all times. As an object moves in a circle, it is constantly changing its direction. Merry-go-round is an example of uniform circular motion. Satellites orbiting our Earth, artificial satellites or our moon, have motions that are very nearly uniform circular motion. The planets that orbit our Sun have motions that are very nearly uniform circular motion. Did you know? Sir Isaac Newton is one of the most influential scientists of all time. He came up with numerous theories and contributed ideas to many different fields, including physics, mathematics, and philosophy. Born in England, Isaac Newton was a highly influential physicist, astronomer, mathematician, philosopher, alchemist, and theologian. Newton's 3 laws of motion relate the forces acting on a body to its motion. Johannes Kepler helped lead a scientific revolution in the 17th century with his amazing work in the field of astronomy. Among his many contributions were the 3 laws of planetary motion. Summary. Let us summarize what we have learned. Motion is a change of position. It can be described in terms of the distance moved or the displacement. The motion of an object could be uniform or non-uniform depending on whether its velocity is constant or changing. The speed of an object is the distance covered per unit time, and velocity is the displacement per unit time. The acceleration of an object is the change in velocity per unit time. Uniform and non-uniform motions of objects can be shown through graphs. The motion of an object moving at uniform acceleration can be described with the help of three equations, namely v is equal to u plus at, s is equal to ut plus 1 upon 2at square, 2as is equal to v square minus u square, where u is initial velocity of the object which moves with uniform acceleration a for time t, v is its final velocity, and s is the distance it travelled in time t. If an object moves in a circular path with uniform speed, its motion is called uniform circular motion. Introduction. Every time we move something, use our pencil or walk, we are using force. Think about how many times you would lose your papers if inertia didn't make it stay where you put it. Objectives. At the end of this lesson, you'll be able to define force, distinguish between balanced and unbalanced force, Newton's law of motion, relation between force and the state of motion attained by it, understand the conservation of momentum. Force and its types. The object will undergo change in its direction, speed, or shape only if force acts on it. Hence, force is defined as: force is any influence that causes an object to undergo a change in speed, a change in direction, or a change in shape. Force is a vector quantity. Force is of two types: balanced and unbalanced. Balanced force means two forces are acting on opposite sides of the body, and that body does not change its position. Example: a block pushed from both the sides with equal force. Unbalanced force is one that is not opposed by an equal and opposite force to cause a change in the object's position. Example: when block with great force on one side. Newton's first law of motion. The book will not move by itself. It will change its state of rest only when force of hand acts on it. This explains us the first law of motion. First law of motion states that a body will remain at rest and a body will remain in motion until and unless external force acts on it. Application of Newton's first law of motion. When a bus starts suddenly, the passengers fall backward because of inertia. The passenger tends to remain in the state of rest even if the bus has started moving. Inertia is the property of the body due to which it resists the change in its state of rest or of uniform motion. Mass is the measure of the inertia of a body. Larger the mass, greater is the inertia. Example: when the car stops suddenly, the driver is jerked forward because of inertia. The passenger tends to remain in state of motion even if the bus has stopped moving. Newton's second law of motion. Newton's second law of motion states that the force acting on the body is directly proportional to the mass of the body and acceleration produced in the body in the direction of the force applied. F is equal to m into A, where F is equal to force, m is equal to mass, A is equal to acceleration. Units of force. The SI unit of force is Newton. Newton is defined as the force acting on the body of mass 1 kg, producing an acceleration of 1 meter per second square. Unit is equal to kilogram meter per second square, or Newton. To calculate force of body having mass 1000 kg and acceleration of 0.5 meter per second square, then F is equal to 1000 into 0.5, which is equal to 500 Newton, or kilogram meter per second square. Application of Newton's second law of motion. Cricket player lowers his hands along with the ball to catch it because the acceleration of the ball gets reduced, and hence overall smaller force is applied to stop the ball and no injury is caused to the hands of the player. Momentum. Momentum is mass in motion. P is equal to m into v, where P is equal to momentum, mass is equal to mass of the body, v is equal to velocity of the body. SI unit is kilogram meters per second. Hence, combined effect of mass and velocity is called momentum. It is a vector quantity. The change of momentum of an object is proportional to the applied unbalanced force in direction of force. Formulation of second law of motion. The change of momentum of an object is proportional to the applied unbalanced force in direction of force. Let the initial momentum be P1, which is equal to mu. Let the final momentum be P2, which equals mv. The change in momentum is P2 minus P1, which equals mv minus mu. Rate of change of momentum is m into v minus u whole upon t. Force is equal to k into m into v minus u whole upon t. Force is equal to kma, where k is the proportionality constant. Newton's third law of motion. Whenever one body exerts a force on another body, the second body exerts an equal and opposite force on the first body. Every action has equal and opposite reaction. Examples to illustrate Newton's third law of motion. How do we walk? When we walk on the ground, our foot pushes the ground backward, and in return, the ground pushes our foot forward. Why the cannon recoil? When ball is fired from a cannon, the force sends the ball forward and is equal to the force sending the cannon backward, hence the cannon is said to be recoiled. Jet aeroplanes and rockets. The action of the gases downwards of the rocket gives equal and opposite reaction to the rocket to move upward with great speed. The case of hose pipe. The fireman directs a powerful stream of water. They hold it tightly because it has tendency to go backward due to the backward reaction of water rushing in forward direction. Law of conservation of momentum. When two or more bodies act upon each other, their total momentum remains constant when no external force exerts on it, is called law of conservation of momentum. Momentum is never created or destroyed. It is also called principle of conservation of momentum. Let two objects of mass ma and mb traveling in the same direction have initial velocities as ua and ub respectively, and their final velocities be va and vb respectively. The rate of change of momentum of ball A be FAB, which is equal to MA into VA minus UA upon T. The rate of change of momentum of ball B FBA is equal to MB into VB minus UB upon T. According to the third law of motion, every action has equal and opposite reaction. Hence, the force exerted when both objects get coiled is FAB is equal to minus FBA. On solving, we have MAUA plus MBUB is equal to MAVA plus MBVB, where MAUA plus MBUB is the total momentum before collision and MAVA plus MBVB is the total momentum after collision. The sum of the momenta of the two objects before collision is equal to the sum of the momenta after the collision when no external unbalanced force acts on it. Momenta is the plural form of momentum. Did you know Sir Isaac Newton sought to describe the motion of all objects using the concepts of inertia and force, and in doing so, he found that they obey certain conservation laws. Equilibrium occurs when the resultant force acting on a point particle is zero. In systems where objects are moving with different velocities, it is impossible to determine which object is in motion and which object is at rest. In other words, to phrase matters more technically, the laws of physics are the same in every inertial frame of reference, that is, in all frames related by a Galilean transformation. Weightlessness when in free-fall orbit around the Earth and Newton's law of motion are more easily discernible in such environments. Summary. Let us summarize what we have learned. First law of motion. An object will be in the state of rest or in motion until external force acts on it. The mass of the object is a measure of inertia. Force of friction always opposes the motion of objects. Second law of motion. The rate of change of momentum of the object is proportional to the unbalanced force in the direction of force applied. The SI unit of force is kilogram meter per second square. Third law of motion. Every action has equal and opposite reaction. The total momentum is always conserved. Introduction. If we raise a body above the ground and then release it, the body falls down towards the earth due to the force which must be acting on it. The force acts due to force of attraction between the earth and the body, which is called force of gravity. As per the example, the ball thrown upward will fall downwards due to gravitational pull or force of gravitation. Gravitation causes variation of weight of a body, varies from place to place. This would be well understood by studying gravitational phenomenon. Objectives. At the end of this lesson, you'll be able to define force of gravitation, define universal law of gravitation, understand the meaning of free fall, distinguish between weight and mass, understand thrust and pressure, understand the Archimedes principle. Force of gravitation. The gravitational pull. Everything is pulled downwards towards the earth. The force with which two objects attract each other is called force of gravitation. The force of gravitation acts even if the two objects are not connected to each other. Centripetal force. The force due to which the body moves along the circular path acting towards the center of the earth is called centripetal force. The gravitational force between the sun and the earth keeps the earth in uniform circular motion around the sun. This is the centripetal force which acts between the earth and sun. Universal law of gravitation. Everybody in the universe attracts every other body with a force which is directly proportional to the product of their masses and inversely proportional to the square of the distance between them. Force is directly proportional to the product of their masses. Force is inversely proportional to the square of the distance of separation between the two objects, where g is the universal gravitational constant and the SI unit is Newton. Universal law of gravitation is also known as Newton's law of gravitation. Unit and value of gravitational constant. By arranging the expression for force of gravitation, we have g is equal to F into r square upon m1 into m2. SI unit is Newton meter square per kilogram square or Newton meter square per kg square. The gravitational constant g is equal to the force of gravitation which exists between the two bodies of unit masses kept at a distance from each other. The value of universal gravitational constant is g is equal to 6.67 into 10 raised to the power minus 11 Newton meter square per kg square. Importance of universal law of gravitation. The force binds the earth, the motion of the moon around the sun, and the tides due to the moon and the sun. Free fall. Our earth attracts all the objects which are near its surface so that when a body is dropped from the roof of a house, it falls down to the earth. The acceleration produced in the freely falling bodies is the same for all the bodies and it does not depend upon the mass of the falling body. Acceleration due to gravity. The uniform acceleration produced in a freely falling body is due to the gravitational pull of the earth is called acceleration due to gravity. The value of acceleration due to the gravity is 9.8 meter per second square. Force is equal to mass into acceleration, which is equal to m into g, equation 1. Force due to gravitation. F is equal to m1 into m2 g upon r square, equation 2. From equation 1 and 2, m into g is equal to m1 into m2 g upon r square. G is equal to gm upon r square. G is equal to 9.8 meter per second square. Difference between weight and mass. Mass. The mass of the body is the quantity of matter contained in it. The mass of the body is constant and does not change from place to place. It is denoted by small m. Mass of the body is a measure of inertia of the body. Mass cannot be zero. Weight. The weight of the body is the force with which it is attracted towards the center of the earth. The weight of the body depends upon the mass of the body and acceleration due to gravity at that place. Weight is Newton. 1 kilogram weight is that gravitational force which acts on a body of mass 1 kilogram. Weight is not constant. The weight can be zero at the center of the earth. Equation of motion for freely falling bodies. The three equations of motion of freely falling bodies is given as V is equal to U plus gt, S is equal to ut plus 1 upon 2 gt square, V square is equal to U square plus 2 gs. Acceleration due to gravity for free falling body is plus 9.8 meter per second square. Acceleration due to gravity for a body thrown upwards is minus 9.8 meter per second square. Weight of an object on the moon is 1 upon 6th. Thrust and pressure. Thrust. The force acting on a body perpendicular to its surface is called thrust. Thrust is equal to pressure into area. The SI unit is Newton. Pressure. The force acting perpendicularly on a unit area of the object is called pressure. Force produces less pressure if the area is large and produces large pressure if the area is small. Pressure is equal to force upon area. The SI unit is newtons per square meter. Uses of pressure in everyday life. The school bags have white stripes because the weight will fall over large area and will reduce its pressures on the shoulders. The tip of the needle is sharp because it will put the force on a very small area of the cloth and producing enough pressure to pierce the cloth being stitched. Pressure on ground is more when a man is walking than when he is standing, because when he is walking, the weight of man falls on smaller area and it increases the pressure, and when he is standing, the area is large and it produces less pressure. Buoyancy. The upward force acting on an object immersed in a liquid is called buoyant force. The upward force exerted by a liquid is also known as upthrust. The tendency of a liquid to exert an upward force on an object placed in it is called buoyancy. Factors affecting the buoyant force depends upon the volume of the solid object immersed in the liquid. It depends upon the density of the liquid in which the object is immersed. Archimedes' principle. When an object is wholly or partially immersed in a liquid, it experiences a buoyant force which is equal to the weight of liquid displaced by the object. The applications are used in designing ships and submarines, lacometers and hydrometers. Buoyant force is equal to weight of liquid displaced by the object. The magnitude of buoyant force is equal to the weight of liquid displaced by the immersed object. Relative density. It is defined as the ratio of the density of a substance to the density of water. It has no unit. Relative density is equal to density of substance upon density of water. Did you know Newton's law of gravitation helps us to find the mass of the earth accurately? Newton's law of gravitation helps us to find the masses of the sun, the moon, and the planets. Gravitation is one of the four fundamental interactions of nature, along with electromagnetism and the nuclear strong force and weak force. Every planetary body, including the Earth, is surrounded by its own gravitational field, which exerts an attractive force on all objects. Summary. Let us summarize what we have learned. The force of attraction between any two objects is proportional to the product of their masses and inversely proportional to the square of the distance between them. Gravitation is a weak force unless large masses are involved. The force of gravity decreases with altitude. The weight is equal to the product of mass and acceleration due to gravity. The weight may vary from place to place. The weight of an object on the moon is 1/6 of that on the earth. When objects are immersed in fluid, they exert a force of buoyancy. Introduction.
I have to do lots of work. I'm so tired. I don't have any more energy now.
Mom, why do you need energy?
Son, we do lots of work daily. Reading, writing, thinking, cycling, etc. So we need energy to do all these activities.
Mom, this washing machine also does work. Does this also need energy?
Yes, but there's a difference. Come, I will tell you about the work and the energy.
Objectives. At the end of this lesson, you'll be able to define work and energy, write different forms of energy, write the expression for kinetic and potential energy, understand the laws of conservation of energy, define power, write the units of work, energy and power. Work. Friends, we do lots of work like playing, studying, cycling, running, etc. All these works require a lot of energy. But the scientific definition of hard work may involve very little work. Let's see how. Look at this huge truck. We work hard to push it, but the truck does not move despite all the effort. We get tired. However, we have not done any work on the truck as there is no displacement of the truck. We can say that we did hard work, but in science the work is not done on the truck. We use and define the term work differently in science. For example, if we climb up a cliff, then according to science, we have done lots of work. Scientific conception of work. For work to be done, these two conditions should be satisfied. First is, a force should act on an object. Second is, the object must be displaced. Let's take a look at a few situations. If we pull a table and the table moves through a distance, here we have exerted a force on the table and it is displaced. So both the conditions are satisfied here. Therefore, work is done. Similarly, while playing cricket, if we hit a ball with a bat, then work is done because force is exerted on the ball and that ball is displaced. Work done by a constant force. To understand the concept of work in science, let us consider a case. Case is, the force is acting in the direction of displacement. Let a constant force F act on an object. Let the object be displaced through a distance s in the direction of the force. Let W be the work done. We define work to be equal to the product of the force and displacement. Work done is equal to force into displacement, or W is equal to F into S. Thus, work done by force acting on an object is equal to the magnitude of the force multiplied by the distance moved in the direction of the force. Work has only magnitude and no direction. If F is equal to 1N and S is equal to 1M, then the work done by the force will be 1 Nm. The unit of work is Newton meter or joule. Thus, 1 Newton meter or 1 joule is the amount of work done on an object when a force of 1 Newton displaces it by 1 meter along the line of action of the force. Example. Let's now find the work done when force applied and displacement is given. A student lifts his school bag from the ground and puts it on his shoulders, 1.5 meter above the ground. A force of 5 Newton is acting on an object. Calculate the work done by him on the school bag. We can see that here force applied is 5 Newton and displacement S is 1.5 meter. We know that work done is equal to force into displacement. Therefore, we get work done is equal to 7.5 Newton meter or 7.5 joule. Energy. We now know that to do any kind of work, we need energy. We must have energy to accomplish work, but the question is, where does this energy come from? The sun is the biggest natural source of energy to us. Many of our energy sources are derived from the sun. Energy sources are classified into two groups: non-renewable and renewable. Most of our energy comes from non-renewable energy sources: coal, petroleum, natural gas, propane, and uranium are non-renewable energy sources. They are used to make electricity, to heat our homes, to move our cars, and to manufacture all kinds of products. These energy sources are called non-renewable because their supplies are limited. Renewable energy sources include biomass, geothermal energy, hydropower, solar energy, and wind energy. They are called renewable energy sources because they are replenished in a short time. We use renewable energy sources mainly to make electricity. An object having a capability to do work is said to possess energy. The object which does the work loses energy, and the object on which the work is done gains energy. The energy possessed by an object is thus measured in terms of its capacity of doing work. The unit of energy is, therefore, the same as that of work, that is, joule. 1 joule is the energy required to do 1 joule of work. Sometimes a larger unit of energy called kilojoule is used. 1 kilojoule equals 1000 joules. Forms of energy. There are many different forms of energies. These various forms include potential energy, kinetic energy, heat energy, chemical energy, electrical energy, and light energy. Let us first study about kinetic energy. We know that a moving object can do work, and an object moving faster can do more work than an identical object moving relatively slow. Kinetic energy is the energy possessed by an object due to its motion. The kinetic energy of an object increases with its speed. Turning wheel, moving car, boy running are the examples of kinetic energy. So we say that the kinetic energy of a body moving with a certain velocity is equal to the work done on it to make it acquire that velocity. Equation of kinetic energy. Let us now express the kinetic energy of an object in the form of an equation. Consider an object of mass m moving with a uniform velocity u. Let it now be displaced through a distance s when a constant force F acts on it in the direction of its displacement. We know that the work done W is Fs. The work done on the object will cause a change in its velocity. Let its velocity change from u to v. Let a be the acceleration produced. The relation connecting the initial velocity u and final velocity v of an object moving with a uniform acceleration a and the displacement s is v square minus u square equal to 2as. This gives s is equal to v square minus u square whole upon 2a. We know that F is equal to ma, so by using values of F and S in the equation of work, we get W is equal to ma into v square minus u square whole upon 2a. Or we can write it as W is equal to 1 upon 2 into m into v square minus u square. If the object is starting from its stationary position, this is u is equal to 0, then the work done, W is equal to 1 upon 2 into mv square. It is clear that the work done is equal to the change in the kinetic energy of an object. Thus, the kinetic energy possessed by an object of mass m and moving with a uniform velocity v is 1 upon 2 mv square. Example. Let's now find the kinetic energy of an object of mass 10 kg which is moving with a uniform velocity of 4 meter per second. Solution. Here mass of the object m is equal to 10 kilogram. Velocity of the object v is equal to 4 meter per second. From equation of kinetic energy we get 1 upon 2 into 10 kilogram into 4 meter per second into 4 meter per second, which is equal to 80 joules. Hence, the kinetic energy of the object is 80 joules. Potential energy. To understand potential energy, let's do an activity. Take a rubber band. Hold it at one end and pull from the other. You will see that the band stretches. Now release the band at one of the ends. What do you see? The band will tend to regain its original length. This means that the band had acquired energy in its stretched position. Do you know how did it acquire energy when stretched? Here the energy gets stored due to the work done on the object. The energy transferred to an object is stored as potential energy if it is not used to cause a change in the velocity or speed of the object. We transfer energy when we stretch a rubber band. The energy transferred to the band is its potential energy. The potential energy possessed by the object is the energy present in it by virtue of its position or configuration. Potential energy of an object at a height. Gravitational potential energy is the energy stored in an object as the result of its vertical position or height. Let's find out the expression for the gravitational potential energy of an object at a height. Consider an object of mass m. Let it be raised through a height h from the ground. A force is required to do this. The minimum force required to raise the object is equal to the weight of the object. The object gains energy equal to the work done on it. Let the work done on the object against gravity be W. That is, work done, W, is equal to force into displacement, which is equal to mg into h, which is equal to mgh. Since work done on the object is equal to mgh, an energy equal to mgh units is gained by the object. This is the potential energy of the object. Also, the work done by gravity depends on the difference in vertical heights of the initial and final positions of the object and not on the path along which the object is moved. Conversion of energy. Answer one question now. Can we convert energy from one form to another? Yes, one form of energy can be converted into another form. Let's take a small example. When we switch on a bulb, the electric energy is converted into light energy. Similarly, when we plug on the TV, the electric energy converts into heat energy, sound energy, and light energy. Laws of conservation of energy. We now know that the form of energy can be changed from one form to another. Whenever energy gets transformed, the total energy remains unchanged. This is the law of conservation of energy. According to this law, energy can only be converted from one form to another. It can neither be created nor be destroyed. The total energy before and after the transformation remains the same. Let us consider a simple example. Let an object of mass m be made to fall freely from a height h. At the start, the potential energy is mgh and kinetic energy is 0. Why is the kinetic energy 0? It is 0 because its velocity is 0. The total energy of the object is thus mgh. As it falls, its potential energy will change into kinetic energy. If v is the velocity of the object at a given instant, the kinetic energy would be 1 upon 2 mv square. As the fall of the object continues, the potential energy would decrease while the kinetic energy would increase. When the object is about to reach the ground, h is equal to 0 and v will be the highest. Therefore, the kinetic energy would be the largest and potential energy the least. However, the sum of the potential energy and kinetic energy of the object would be the same at all points. That is, potential energy plus kinetic energy is equal to constant, or mgh plus 1 upon 2 mv square is equal to constant. The sum of kinetic energy and potential energy of an object is its total mechanical energy. We find that during the free fall of the object, the decrease in potential energy at any point in its path appears as an equal amount of increase in kinetic energy. There is thus a continual transformation of gravitational potential energy into kinetic energy. Rate of doing work. Consider two children, say A and B. Let us say they are of the same age. Both start swimming separately. Let us say A takes 5 minutes while B takes 9 minutes to accomplish the task. They did the same work, but A has taken less time than B to do the work. This means that a stronger person may do certain work in relatively less time. Similarly, a more powerful vehicle would complete a journey in a shorter time than a less powerful one. So, power is defined as the rate of doing work or the rate of transfer of energy. If an agent does a work W in time t, then power is given by power is equal to work upon time, or P is equal to W upon T. The unit of power is watt, having the symbol W. 1 watt is the power of an agent which does work at the rate of 1 joule per second. We can also say that power is 1 watt when the rate of consumption of energy is 1 joule per second. 1 watt is equal to 1 joule per second. We express larger rates of energy transfer in kilowatts. 1 kilowatt is equal to 1000 watts. 1 kilowatt is 1000 joule per second. Commercial unit of energy. We know the unit of energy is joule, but the large quantities of energy cannot be expressed by the unit joule. For that we use a bigger unit of energy called kilowatt. Let us take an example of a machine that uses 1000 joule of energy every second. If this machine is used continuously for 1 hour, it will consume 1 kilowatt hour of energy. Thus, 1 kilowatt hour is the energy used in 1 hour at the rate of 1000 joule per second, or 1 kilowatt. So, 1 kilowatt hour is equal to 1 kilowatt into 1 hour is equal to 1000 watt into 3600 S, which is equal to 36 lakh joule. 1 kilowatt hour is equal to 3.6 into 106 joule. The energy used in our houses and big industries are usually expressed in kilowatt hour. Did you know? James Prescott Joule was an outstanding British physicist. He is best known for his research in electricity and thermodynamics. Amongst other things, he formulated a law for the heating effect of electric current. He also verified experimentally the law of conservation of energy and discovered the value of the mechanical equivalent of heat. The unit of energy and work, called joule, is named after him. The potential energy of an object at a height depends on the ground level or the zero level you choose. An object in a given position can have a certain potential energy with respect to one level and a different value of potential energy with respect to another level. Summary. Let us summarize what we have learned. Work done on an object is defined as the magnitude of the force multiplied by the distance moved by the object in the direction of the applied force. The unit of work is joule. 1 joule is equal to 1 Newton into 1 meter. An object having capability to do work is said to possess energy. Energy has the same unit as that of work. An object in motion possesses the kinetic energy of the object. An object of mass m moving with velocity v has a kinetic energy of 1 upon 2 mv square. The energy possessed by a body due to its change in position or shape is called the potential energy. The gravitational potential energy of an object of mass m raised through a height h from the Earth's surface is given by mgh. According to the law of conservation of energy, energy can only be transformed from one form to another. It can neither be created nor destroyed. The total energy before and after the transformation always remains constant. The sum of the kinetic and potential energies of an object is called its mechanical energy. Power is defined as the rate of doing work. The SI unit of power is watt. 1 watt is equal to 1 joule per second. The energy used in 1 hour at the rate of 1 kilowatt is called 1 kilowatt hour.
Introduction.
Hey Pinky, let's go back. I have to study. No, wait. Come, I will show you something. What? Say something loudly. Pinky! Wow, what is this? This is called the echo. Echo? Interesting. Yes, echo of the sound. Do you want to know more about this? Yes. Yes, please tell me. Come, today I will tell you everything about sound.
Objectives.
At the end of this lesson, you will be able to understand the production of sound, understand the propagation of sound, write the characteristics of sound waves, understand the reflection of sound, define echo and reverberation, describe sonar, and explain the structure of human ear. Production of sound. Students, we know that sound is a sensation or a feeling that we hear. Sound is produced with a vibrating object. The motion of materials or objects causes vibrations. Vibration means a kind of rapid to and fro motion of an object. Let us look at some examples of how certain sounds are produced. Human voice. The sound of the human voice is produced due to vibrations in the vocal cords. Animal sound. When a bird flaps its wings, a sound is produced. Bees buzz as they fly because of the rapid movement of their wings. Their wings make the air vibrate, producing a buzzing sound. Musical sounds. Musical instruments produce many different sounds in various ways. Some instruments need to be struck by an object in order to produce a sound, while some instruments, such as a harp or a violin, produce sounds when one or more of their strings are plucked, causing them to vibrate. Propagation of sound. For sound to be generated and heard, it must have three things. They are a source, a medium through which to pass, and a receiver. Let us assume the source is the speaker's voice. The medium through which it is transmitted is air, and the receiver is the listener's ear. When a sound is generated by the speaker's speech, or when an object vibrates, it sets the particle of the medium around it vibrating. The particles do not travel all the way from the vibrating object to the ear. A particle of the medium in contact with the vibrating object is first displaced from its equilibrium position. It then exerts a force on the adjacent particle, which gets displaced from its position of rest. After displacing the adjacent particle, the first particle comes back to its original position. This process continues in the medium till the sound reaches your ear. During propagation of sound in a medium, the particles of the medium do not move forward themselves, but the disturbance is carried forward. So, sound waves are characterized by the motion of particles in the medium and are called mechanical waves. Can you tell the most common medium of sound? Air is the most common medium through which sound travels. When a vibrating object moves forward, it pushes and compresses the air in front of it, creating a region of high pressure. This region is called a compression. And when the vibrating object moves backwards, it creates a region of low pressure called rarefaction. The compressions are regions of high air pressure, while the rarefactions are regions of low air pressure. Look at this image. It shows a sound wave created by a tuning fork and propagated through the air in an open tube. These are the regions of compression, and these are the regions of rarefaction. Sound needs a medium to travel. As sound is created by the vibration of particles, it requires a medium such as air, liquid, or a solid. But how can we prove that it needs medium to travel? Let's see. Look at this figure. Here, an electric bell is suspended inside an airtight glass bell jar connected to a vacuum pump. As the electric bell circuit is completed, the sound is heard. Now, if we slowly remove the air from the bell jar by using a vacuum pump, the intensity of sound goes on decreasing, and finally, no sound is heard when all the air is drawn out. We would be seeing the hammer striking the gong repeatedly. This clearly proves that sound requires a medium for its propagation. Sound waves are longitudinal waves. A wave in which the particles of the medium vibrate back and forth in the same direction in which the wave is moving is called a longitudinal wave. Longitudinal wave can be produced in all the three mediums: solids, liquids, and gases. Sound waves are longitudinal because the direction of vibration of the particles is parallel to the direction of wave. When a sound wave passes through air, the particles of air vibrate back and forth parallel to the direction of sound wave. Thus, when a sound wave travels in the horizontal direction, then the particles of the medium also vibrate back and forth in the horizontal direction, but parallel to the direction of sound. For example, the waves produced in air when a violin wire is plugged are longitudinal waves. There is also another type of wave called a transverse wave. A transverse wave is the one in which the individual particles of the medium move about their mean positions in a direction perpendicular to the direction of wave propagation. Characteristics of a sound wave. A sound wave can be described by three basic qualities, that is, its frequency, amplitude, and speed. The number of times the wavelength occurs in 1 second is called frequency. It is measured in kilohertz or cycles per second. The faster the sound source vibrates, the higher the frequency. Higher frequencies are interpreted as a higher pitch. For example, when you sing in a high-pitched voice, you are forcing your vocal cords to vibrate quickly. Thus, a high-pitched sound corresponds to more number of compressions and rarefactions passing a fixed point per unit time. Objects of different sizes and conditions vibrate at different frequencies to produce sounds of different pitch. It is usually represented by a Greek letter nu. Its SI unit is Hertz. We know that compressions are the regions where particles are crowded together and represented by the upper portion of the curve. The peak represents the region of maximum compression. Thus, compressions are regions where density as well as pressure is high. Rarefactions are the regions of low pressure where particles are spread apart and are represented by the valley, that is, the lower portion of the curve. A peak is called the crest and a valley is called the trough of a wave. The distance between two consecutive compressions or two consecutive rarefactions is called the wavelength. The wavelength is usually represented by a Greek letter lambda. Its SI unit is meter, m. The time taken by two consecutive compressions or rarefactions to cross a fixed point is called the time period of the wave. It is represented by the symbol t. Its SI unit is second. Frequency and time period are related as nu is equal to 1 upon t. The strength or power of a wave signal is called its amplitude, or the height of the wave when viewed as a graph is the amplitude. The loudness or softness of a sound is determined basically by its amplitude. The amplitude of the sound wave depends upon the force with which an object is made to vibrate. Speed. The speed of sound is defined as the distance with which a point on a wave, such as a compression or a rarefaction, travels per unit time. We know that speed, u is equal to distance upon time, which is equal to lambda upon t. Here, lambda is the wavelength of the sound wave. It is the distance travelled by the sound wave in one time period of the wave. Thus, u is equal to lambda into nu. That is, speed is equal to wavelength into frequency. Speed of sound in different media. The speed of sound depends on the material through which it's passing. It is greater in solids than in liquids or gases because the molecules in a solid are closer than in a liquid or gas. In this table, you can find the speed of sound in different media at 25 degrees Celsius. Reflection of sound. Like light, sound also gets reflected at the surface of a solid or liquid. The reflection of sound follows the same laws as for reflection of light. Angle of incidence is equal to the angle of reflection. The incident wave, reflected wave and the normal lie in the same plane. Sound waves can be reflected by large, hard, smooth, vertical and faraway surfaces. Example, walls, buildings and cliffs. Echoes are produced by the reflection of sounds from such surfaces. The sensation of sound persists in our brain for about 0.1 second. To hear a distinct echo, the time interval between the original sound and the reflected one must be at least 0.1 second. If we take the speed of sound to be 344 meter per second at a given temperature, say 22 degrees Celsius in air, the sound must go back to the obstacle and reach back the ear of the listener on reflection after 0.1 second. Hence, the total distance covered by the sound from the point of generation to the reflecting surface and back should be at least 344 meter per second into 0.1 second is equal to 34.4 meters. Thus, for hearing distant echoes, the minimum distance of the obstacle from the source of sound must be half of this distance, that is 17.2 meters. This distance will change with the temperature of air. Echoes may be heard more than once due to successive or multiple reflections. Reverberation. The repeated reflection that results in this persistence of sound is called reverberation. A reverberation is perceived when the reflected sound wave reaches your ear in less than 0.1 second after the original sound wave. For example, a sound created in a big hall will persist by repeated reflection from the walls until it is reduced to a value where it is no longer audible. Let's now solve a problem. A person shouts near a cliff and hears the echo after 5 seconds. What is the distance of the cliff from the person if the speed of the sound, v, is taken as 300 meters second raised to the power minus 1? Given that the speed of sound, v, is 300 meter second raised to the power minus 1. Time taken for hearing the echo, t, is 5 seconds. Distance travelled by the sound is equal to v into t, which is equal to 300 meter second raised to the power minus 1 into 5 seconds is equal to 1500 meters. In 5 seconds, sound has to travel twice the distance between the cliff and the person. Hence, the distance between the cliff and the person is 1500 meters by 2, that is 750 meters. Range of hearing. The average person has a normal hearing range that falls between 20 Hz on the low side and approximately 20,000 Hz on the high side. Children under the age of 5 and some animals such as dogs can hear up to 25 kHz. The hearing range of humans gets worse with age. People lose the ability to hear sounds of high frequency as they grow older. Sounds of frequencies below 20 Hz are called infrasonic sound or infrasound. Some animals like whales and elephants produce sounds in the infrasound range. Frequencies higher than 20 kHz are called ultrasonic sound or ultrasound. Dogs can hear some ultrasound, thus a dog trainer can use an ultrasound whistle to call his dog. Ultrasound is even more important for bats because they rely on ultrasound to see the world. Applications of ultrasound. We use ultrasounds in industries and for medical purposes. Ultrasounds are able to travel along well-defined paths, even in the presence of obstacles. The doctors use a high-frequency ultrasound handheld transducer to scan the mother's abdomen. It is generally used to clean parts located in hard-to-reach places, for example, spiral tube, odd-shaped parts, electronic components, etc. Ultrasounds can be used to detect cracks and flaws in metal blocks. Ultrasonic waves are allowed to pass through the metal block and detectors are used to detect the transmitted waves. If there is even a small defect, the ultrasound gets reflected back, indicating the presence of the flaw or defect. Ultrasound is used for echocardiography. In this, the ultrasonic waves are made to reflect from various parts of the heart and form the image of the heart. Ultrasound is also used to break small stones formed in the kidneys into fine grains. These grains later get flushed out with urine. Sonar. Sonar is the device that uses ultrasonic waves to measure the distance, direction, and speed of underwater objects. The word sonar stands for sound navigation and ranging. Sonar consists of a transmitter and a detector and is installed in a boat or a ship. The transmitter produces and transmits ultrasonic waves. These waves travel through water and after striking the object on the seabed get reflected back and are sensed by the detector. The detector converts the ultrasonic waves into electrical signals which are appropriately interpreted. The distance of the object that reflected the sound wave can be calculated by using echo ranging method. Let the time interval between transmission and reception of ultrasound signal be t and the speed of sound through seawater be v. The total distance 2d travelled by the ultrasound is then 2d is equal to v into t. This is the echo ranging method. Structure of the human ear. The ear consists of three basic parts: the outer ear, the middle ear, and the inner ear. Each part of the ear has a specific role in the task of detecting and interpreting sound. The outer ear is called pinna. It collects the sound from the surroundings. The collected sound passes through the auditory canal. At the end of the auditory canal, there is a thin membrane called the eardrum or tympanic membrane. The eardrum moves inward and outward as the compression or rarefaction reaches it. In this way, the eardrum vibrates. These vibrations are amplified by the three bones, namely the hammer, anvil, and stirrup in the middle ear. The middle ear transmits these vibrations to the inner ear. Inside the inner ear, the vibrations or the pressure variations are converted into electrical signals by the cochlea. These electrical signals are sent to the brain via the auditory nerve and the brain interprets them as sound. Did you know? Heinrich Rudolf Hertz was born on 22nd February 1857 in Hamburg, Germany, and educated at the University of Berlin. He confirmed J.C. Maxwell's electromagnetic theory by his experiments. He laid the foundation for future development of radio, telephone, telegraph, and even television. He also discovered the photoelectric effect, which was later explained by Albert Einstein. The SI unit of frequency was named as Hertz in his honor. Hearing aid. People with hearing loss may need a hearing aid. A hearing aid is an electronic, battery-operated device. The hearing aid receives sound through a microphone. The microphone converts the sound waves to electrical signals. These electrical signals are amplified by an amplifier. The amplified electrical signals are given to a speaker of the hearing aid. The speaker converts the amplified electrical signal to sound and sends to the ear for hearing. Summary. Let us summarize what we have learned. Sound is produced due to vibration of different objects. Sound travels as a longitudinal wave through a material medium. Sound travels as successive compressions and rarefactions in the medium. Sound cannot travel in vacuum. The distance between two consecutive compressions or two consecutive rarefactions is called wavelength, lambda. The time taken by the wave for one complete oscillation of the density or pressure of the medium is called the time period, t. The number of complete oscillations per unit time is called the frequency, nu is equal to 1 upon t. The speed u, frequency nu, and wavelength lambda of sound are related by the equation u is equal to lambda into nu. The speed of sound depends primarily on the nature and the temperature of the transmitting medium. The law of reflection of sound states that the directions in which the sound is incident and reflected makes equal angles with the normal to the reflecting surface, and the three lie in the same plane. For hearing a distinct sound, the time interval between the original sound and the reflected one must be at least 0.1 second. The persistence of sound in an auditorium is the result of repeated reflections of sound and is called reverberation. The audible range of hearing for average human beings is in the frequency range of 20 Hz to 20 kHz. Sound waves with frequencies below the audible range are called infrasonic, and those above the audible range are termed ultrasonic. Ultrasound has many medical and industrial applications. The sonar technique is used to determine the depth of the sea and to locate underwater hills, valleys, submarines, icebergs, sunken ships, etc.